This is our second video. This one is on angles and trigonometric functions. Remember from geometry that we have trigonometric functions. You learned about sine, cosine, and tangent, and you might have touched on cosecant, secant, and cotangent a little bit, but we're going to talk about them a lot more in depth this year. There were three trig functions that you spent a lot of time on. Sine of an angle was the opposite side over the hypotenuse. The cosine of an angle was the adjacent side over the hypotenuse, and the tangent of an angle was the opposite side over the adjacent side. So just a reminder, the opposite side is the side that is furthest away from the angle. The adjacent side is the side that's right next to the angle that isn't the hypotenuse. And the hypotenuse is the hypotenuse of the right triangle. So opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. You may have seen SOHCAHTOA a lot last year. Well, this year, we're going to also talk about cosecant, secant, and cotangent. Those are just the reciprocals of each of the functions that they're right next to on our paper. So cosecant of an angle is the hypotenuse over the opposite side. The secant of an angle is the hypotenuse over the adjacent side. And the cotangent of an angle is the adjacent side over the opposite side. So those are things that you just have to kind of memorize. And you hopefully learned sine, cosine, and tangent last year. Well, this year we will start doing those on a coordinate plane. And it's important to know that when we do this on a coordinate plane, we're kind of thinking about it in terms of a circle. And so if I have some sort of triangle that I'm forming, remember I always draw my side of the triangle to the x-axis, and the x-axis forms the other side of the triangle. So that would be an example of a triangle. Here's another example of a triangle. So I have the right angle here, and then I'm drawing it to the x-axis. Here's another example of a triangle. Right angle is formed with the x-axis. Here's another example of a triangle. Right angle formed with the x-axis. So there are a bunch of examples of triangles that we have formed with the x-axis. One thing that we want to keep in mind is remember that our angles are counterclockwise. If I go clockwise, I can have a negative angle, but I don't have to do that. I can go counterclockwise and form angles even if those sides are in the third or fourth quadrant or whatever. So I have this situation. Now, what we've done in the past is we've seen opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. That's still true, but it just so happens that in each of these cases, since the angle that we are forming is with the x-axis, since the angle we're forming is with the x-axis, we're looking at this, 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 and this as my four angles. Since we're finding the angle formed from the x-axis to the terminal side, and we're going to use reference angles to help. So each of these four angles that are like that peach color, while they're not the same, they all have the same properties. And if you notice, the opposite side is always the y value of the point on this circle. So the opposite side is always the y value. So I'm going to replace opposite with y. The adjacent side to this angle is always the x value. That's true in all four of these triangles. So the adjacent side I'm going to replace with x. And the hypotenuse is always the radius of this circle. So that's r. So basically what I'm going to do is I'm going to take all of these things and I'm going to replace opposite, adjacent, and hypotenuse with y, x, and r. So sine of an angle is y over r. Cosine of an angle is x over r. Tangent of an angle is y over x. Cosecant of an angle is r over y. Secant of an angle is r over x. And cotangent of an angle is x over y. So these six things are things that are true about sine, cosine, and tangent when we do them on the coordinate plane. The phrase unit circle comes up a lot. Unit meaning one and circle meaning circle. So when we're talking about the unit circle, that means that the radius of the circle is one. So all of these R values are one. But we don't have to draw it that way all the time when we're trying to figure out what sine, cosine, tangent, cosecant, secant, or cotangent of any functions are. We don't have to draw it with a radius of one or the hypotenuse being one. If we have a unit circle, that has to be one, but it doesn't always have to be a unit circle when we're drawing it. Um, it can be a little bit easier than that. Why do we spend so much time with 30, 60, 90, and 45, 45, 90 triangles in geometry? Because they show up all the time, and they show up all the time in um, in many different math classes, including this one. So if we take an equilateral triangle and we split it down the middle with an altitude. Now, in an equilateral triangle, if you draw an altitude, it's also an angle bisector, a perpendicular bisector, and um, a median. So it does a lot of different things. So we have congruent sides down here. So let's say I had a side length of 2, then that would be 1. This would be 1. And if I did the Pythagorean theorem, 1 squared plus altitude squared equals 2 squared, I'd find out that the altitude is the square root of 3. So that length is the square root of 3. If I have a right triangle that's isosceles with side length 1, and I did the Pythagorean theorem, I'd end up with square root of 2 over here. These things show up all the time. So if I look at a 30, 60, 90 triangle, so if I just kind of pretend like the rest of this isn't here, and I just look at the 30, 60, 90 triangle over on the right side of this, and I look at the 45, 45, 90 triangle, that's stuff that we need to know from our geometry days. And it's also stuff that we're going to use a lot even with radians. So if I have a 30-degree angle, I can convert that to radians, and it'll be pi over 6. So if I look at pi over 6, pi over 3, and pi over 2, I have the exact same situation that I have in a 30, 60, 90 triangle. Same thing with a 45, 45, 90, and pi over 4. I'm going to use these triangles a lot, even if I have radians. So let's find the following. Sine of pi over 6. Now pi over 6, that is drawn terribly. Pi over 6 is about here on the coordinate plane. Pi over 6 is not up to pi over 2 yet, and it's its own reference angle. Uh, it is a 30-degree or pi over 6 reference angle in the first quadrant. So I can draw this triangle and figure out what sine is. Sine is 1/2 because this is my angle. Opposite over hypotenuse ends up being 1/2. Sine, remember, sine of an angle is also y over r. So if my y value is 1, the y coordinate of this point, being 1. That would be root 3 comma 1, and that length would be 2 if I did the Pythagorean theorem using the distance formula. My y value is 1, and my radius is 2, so I get 1/2. Cosine of 3 pi over 4, so 3 pi over 4 is in the second quadrant, and that's a pi over 4 reference angle, so my reference angle being right here, I would draw 1, 1, square root of 2, and then I'd notice that this is negative. Okay, so what I end up having is my x value is negative here, so my cosine ends up being -1 over root 2, and if I multiply the top and bottom by square root of 2, multiply by the FFU, root 2 over root 2, I end up with negative root 2 over 2 as my answer. Now, one thing that's really important here is that last year when we were doing right triangles, we never had negative values for sine, cosine, tangent, cosecant, or whatever. We never had negative values. Now that we're on a coordinate plane and we're starting to deal with x, y, and r, y and x can be negative because I could have negative x values if I'm going in this direction, or I could have negative y values if I'm going in this direction in the coordinate plane. Therefore, my sine, cosine, and tangent ratios, or cosecant, secant, and cotangent ratios, can be negative. That's important to know. They can be negative. So the ratios can be negative in this case. But my radius or my hypotenuse, I will always learn how to spell. Always treat as positive. So I'm going to always treat the radius or the hypotenuse as positive. Okay, cosecant of 13 pi over 3. So if I'm doing 13 pi over 3, 6 pi over 3 would get me to here. 12 pi over 3 would again get me back to here. And then 13 pi over 3 is going to be in the first quadrant. I don't know if I drew that really well. 13 pi over 3. Yeah, I did. That's fine. So that is up pi over 3 from my x-axis. So my reference angle is pi over 3. So there's the right angle. I'm trying to find this angle here. That's pi over 3. And then I have 1, root 3, and 2 on my triangle. Cosecant of an angle is going to equal the hypotenuse or the radius divided by y, because it's basically the reciprocal of sine. So that's 2 divided by the square root of 3, and I would use a FFU, multiplying the top and bottom by the square root of 3 to get it as a rationalized denominator. So I have 2 root 3 over 3. Cotangent of negative pi over 4, or 5 pi over 4. So 4 pi over 4 will get me to here, and then 5 pi over 4 will get me up there. That ends up making it in the second quadrant. So cotangent is x over y, or adjacent over opposite. Now, if this is a pi over 4 reference angle, 1, 1 square root of 2, notice the y is positive and the x is negative here. So x over y is -1 over 1, which is -1. Tangent of 17 pi over 6, so 17 pi over 6. 12 pi over 6 would get me to here. And then that's another 5 pi over 6. That's going to get me almost to the x-axis on the left side, but not quite. So this is 5 pi over 6 from here to here. And then my reference angle is pi over 6. So now trying to find this. 1 square root of 3 and 2. The x value is negative. So tangent is y over x. Y is 1. X is negative square root of 3. If I multiply by the FFU, root 3 over root 3, I end up with negative square root of 3 over 3. as my answer. Secant of negative 7 pi over 3. Negative means we're going this way. 6 pi over 3 gets me back to where I started, and then another pi over 3 will get negative 7 pi over 3. This is in the fourth quadrant. It's a pi over 3 reference angle. So it's actually negative. It's coterminal with negative pi over 3, or coterminal with 5 pi over 3 if we want to talk about coterminality like we did last time. So that's a 1, that's a negative root 3, and this is a 2. Secant is r over x. So 2 divided by 1 is 2. So secant of negative 7 pi over 3 is 2. Finally, let's find the value of all 6 trig ratios for 5 pi over 6. So 5 pi over 6 is in the second quadrant. We've actually already found tangent for this because we've already drawn this, since 17 pi over 6 is the same thing as 5 pi over 6. So this is a 1, this is a negative square root of 3, and this is a 2. And we're doing this with a pi over 6 reference angle. It's basically the same picture. So sine of 5 pi over 6 is going to be y over r. Y over r is 1/2. Cosine of 5 pi over 6 is negative root 3 over 2. Tangent of 5 pi over 6 is negative root 3 over 3. We already found that. Cosecant of 5 pi over 6 is going to be the reciprocal of sine, so that's 2. It's also r over y, and r over y is 2 over 1. Secant of 5 pi over 6 is going to be 2 divided by negative root 3, which if I did a FFU and multiply the top and bottom by root 3, I'd get negative 2 root 3 over 3. And cotangent of 5 pi over 6 is just negative square root of 3, because that's x over y, and x is negative root 3 divided by 1.